Bismillahirrahmanirrahim. Assalamu alaikum ji. I assume now we have a very good understanding of what do we mean by classification in machine learning, as we have studied kin and classifier. In the next couple of videos, we will talk about how do we analyze and measure the performance of a classifier. We will also talk about multi-class classification and how do we evaluate its accuracy or its performance. The outline for the next couple of videos would be that we will start with this classification accuracy, uh, and then we will define the terms true positive, true negative, false positive, and false negative. Using these terms, we will construct a table, what we call confusion matrix or contingency table, and then from the entries of this matrix, we will define sensitivity, specificity, and precision, and what are trade-offs between these terms. How can we encounter these trade-offs? How can we study these trade-offs? Uh, and then we will talk about F1 score and Matthews correlation coefficient. These are two measures to evaluate the performance of classifier. And finally, we will talk about multi-class classification. How to evaluate a multi-class classifier, and what do we mean by micro and macro averaging in the context of multi-class classification. Okay, let's start with the classification accuracy. We can define accuracy of a classifier using the 0-1 loss function, which we studied in the, I think, the second module, second lecture, in fact. Okay, that's how we defined a 0-1 loss function. So its interpretation is that for any point x, the loss is either 0 or 1. So this quantity here, which is inside a summation, let me, yeah. So this quantity can be either 0 or 1. If the prediction is correct, right, that means h of xi is equal to yi, so delta would be delta subscript 0. When subscript is 0, delta takes a value of 1, and consequently, this quantity would be 0 when the prediction is correct. It means no loss. When the prediction is incorrect, we call it a loss, right? So this quantity can be interpreted as the loss. So this term is either 0 or 1. It depends whether the prediction is correct or incorrect. And when we average over all these n data points we have in the set, so we get this 0-1 loss. And this is, in fact, what we call a a misclassification rate, because this quantity gives the proportion of objects for which classifier is incorrect, for which classifier is wrong, right? Okay. As I said, misclassification rate estimate of the probability that a point is incorrectly classified. Uh, Using misclassification rate, we can define accuracy, which is simply 1 minus misclassification rate, right? Or the quantity that gives the proportion of objects for which the classifier is correct. The classifier is giving you correct predictions. So accuracy quantifies the amount, the proportion of the data for which the classifier is giving you correct predictions. So accuracy, although it is widely used, it does have some drawbacks. And these drawbacks include that we cannot use this accuracy measure when the classes are imbalanced or skewed. What do you mean by this? And let me illustrate this with the help of one example. Okay, we take a very simple example that you build a classifier that predicts if a bowler will not ball a no ball. Right? So it's an example from cricket. As we are a cricket loving nation, we want to build a classifier whether a bowler will not ball a no ball. And we assume that in an inning of 50 overs game, we have 15 no balls. And if you have a model that says yes all the time, that baller will not ball a no ball. So such a classifier will have 95% accuracy, right? Because the total balls would be 15 plus 300, right? So 50 overs, 1 over is 5 balls, sorry, 1 over is 6 balls, 50 times 6, 300, and you have 15 extra balls because 15 are no balls. You have 315 no balls. A model is saying yes all the time. The baller will not ball a no ball. The model would be accurate, in fact, 95% accurate. That is uh, 315 times the classifier is saying a baller will not ball on a wall, right? So there are only 15 misclassifications. Otherwise, the model is working fine, right? So using this accuracy as a performance metric, we can say that a model is very, very accurate, but in fact, the model is not useful or model is not valuable, right? Why? So total points we had 315. We're assuming that there are no other illegal balls, there are no other white balls. So no ball label, I call it class 0. And if the ball is not a no ball, I call it class 1. Right? So if you see the total number of balls, out of those total number of balls, only 5% balls are from class 0 and remaining 95% are from class 1. So we say we have imbalanced classes, right? So in one class, we only have 15 elements. In another class, we have 300 data points. The classes are skewed, the classes are imbalanced. And for skewed classes, as we have just seen, it is misleading to use accuracy to evaluate the performance of the classifier, right? So this is just one demonstration, one example that accuracy is not a good measure to evaluate the performance of the classifier when the classes are skewed, when the classes are imbalanced. In fact, we encounter this imbalancing in all of the applications. For example, we talk about disease detection. Right? So, given some of the reports of a patient, some pathology reports, some scans, you want to detect whether the person is suffering from a particular disease or not. In most of the cases, you would say you expect the person is healthy, right? Right. And so we have imbalancing in classes. Similarly, if you are in finance and you want to detect a fraudulent transaction, so you're encountering thousands of transactions every day, but out of those thousands of transactions, only few are fraudulent. So again, we have skewed classes, right? Okay. For skewed classes, accuracy is not a good measure. So we need to we need to define some other measures to evaluate the performance of classifier. Okay, to handle this, we'll define the terms uh, true positive, true negative, false positive, and false negative. You often hear these terms when you study the literature of machine learning, but let's formally define what you mean by these four quantities. To understand these four terms, we consider a binary classification problem. In fact, they're only defined for a binary classification problem. In a binary classification problem, we have this data set. And what about y? Y can only take values 0 or 1, right? So we have a binary classification problem. So set y would be 0 and 1. So these are the labels we know, right? For these x1, x2, xn, we know the labels y1, y2, yn. In fact, if we know the label, we call them actual labels or ground truth, gold labels or gold standards. So these are different terms used in the literature, that some you call y as actual label of the data point, ground truth, gold label, or a gold standard. We will use 0 as we will refer to 0 as negative and 1 as positive. And this is something very standard. Right? This will help us in defining these terms: true positive, true negative, false positive, and false negative. Okay. For this binary classification problem, we say we have a classifier h of x is equal to y hat. So this classifier takes test point from the feature space as an input and gives you an estimate of the label, or it predicts a label y hat. Again, y hat can be 0 or y hat can be 1. So both y hat and y can be positive or negative. Okay, we say y hat as true if y hat is equal to y, and we say y hat is false if y hat is not equal to y, right? Simple. So if you are predicting y correctly, we call it true. If you're not predicting y correctly, we call it false. So true refers to correct prediction, false refer to incorrect prediction. Positive, class 1, negative, class 0. Okay. So with this understanding, let's move forward and define these terms. Okay. We have true positive, true negative, false positive, false negative. How do you define true positive? Number of points, right? So true and positive. Positive means 1. Number of points with y is equal to 1, and your classifier predicted as 1. True positive. True negative, number of points with gold label 0, gold label negative, and your classifier also predicted as negative because true. True positive, it is positive in actual, you predicted positive. True negative, it's negative in actual and you predicted as negative. What is false positive? So number of points with y is equal to 0, right? But you predicted as positive because it's false positive. You predicted as positive, but that's the false prediction. Similarly, false negative, you predicted as negative, but it's a false prediction. In fact, in actual, it is 1. Okay, so yeah, so false negative, number of points with y is equal to 1, but you classify it as 0. False positive, number of points with y is equal to 0, and you classify it as y hat is equal to 1, and so on and so forth. Okay, so let me illustrate, let me explain these 4 quantities with the help of a couple of examples. Okay, again, we take a same example. We want to build a classifier that predicts if a bowler will not ball a no ball. Right? So we assume that you have a model that has been observing the bowlers for the last 15 years and use these observations for learning. A bowler is going to ball, right? And you know the current situation, the behavior of a bowler for the last 15 years, and you expect that you can predict that whether the bowler will ball a no ball or not. Okay. So if we have 15 no balls in an inning, so we have total 315 balls. As I said earlier, no ball, we call it class 0. A regular ball or a valid ball or legal ball, we call it class 1. Okay. We assume that you have a model that predicted 10 no balls correctly. So we have 10 no balls Out of 15 no balls, but these 10, when model predicted these 10 balls, so 8 were correct predictions and 2 were incorrect predictions, right? And given this information, we want to calculate true positive, true negative, false positive, and false negative. Can you help me in computing this? So true positive means it was a regular ball and your model predicted as a regular ball. So model predicted two incorrect no balls. That means so these two were in fact regular balls. And how many regular balls we have? 300. Right? So out of 300, your model predicted two as no balls, incorrectly predicted. That means the remaining 298 balls have been predicted correctly by a classifier. So true positive would be 298. What about true negative? So negative here, no ball. And you said you could predict 8 correct no balls. So true negative is 8. What about false positive? You predicted as regular balls, but they were in fact no balls. So in total, we had 15 no balls. You predicted 8 correctly. So the false positive would be 7. And what about false negative? 2. Right? So we have true positive 298, true negative 8, false positive 7, and false negative 2. I hope this is clear. Okay. So now using these four quantities, we are going to form a matrix. We will combine these four quantities and represent in the form of a table, what we call contingency table or confusion matrix. Okay, let's talk about confusion matrix. Okay, so that's how a confusion matrix looks like. So let me explain this. Along the rows, we correspond to predicted class and the columns true class. I see. So at top here, I have actual labels, gold labels, gold standards, right? And actual label can be positive, actual label can be negative. Predicted label can be positive or negative. Right? So the quantity here, this is true positive. That means the actual label is positive and you predict it as positive. False positive, you predicted positive, but that's a false prediction. Actually, so those points were negative. F false negative, the number of points with actual label positive, but you predicted as negative. So N indicates, okay, this second is what you predicted, and the first F is if it's a false prediction or it's a true prediction. Similarly, true negative, what's the interpretation? Number of points with y is equal to 0, and you also predicted y hat 0, right? True negative. Okay. If you sum these two terms, TP and FP, true positives and false positives, so what you get is the total number that model predicted as positives. Similarly, if you add false negative and true negative, you get total negatives the model predicted. And if you sum along each column, what you get is actual total positives and actual total negatives. So P denotes the actual total positives in your data, the number of positives or the number of points in your data set with 1 as gold label, and number of points in your data set with 0 as gold label. Okay, I hope this is clear, right? So now if you see a confusion matrix and you see these terms true, positive, true, negative, false, positive, false, negative, uh, uh, you should be able to clearly interpret the results in the table or the information given in the table. Okay, let's learn further, and let me illustrate this with the help of a couple of examples. Okay, we take example from disease detection. So given pathology reports and scans of a patient, we want to predict, your classifier predicts whether the person is suffering from heart disease or not. So if the heart disease is detected, you call it yes. That means positive class, no, 0, negative class. Okay. And you carry out analysis on 165 patients, and you find true positives, true negative, false positive, false negative, and you construct this confusion matrix. Given, okay, if you're given this confusion matrix, how would you interpret this confusion matrix? What is the interpretation of this confusion matrix? Okay, first of all, you would say that P is 105, N is 60. So in total, we had 105 plus 60, 165 patients. We had 165 cases. We had 165 data points. So out of those 165 data points, right? So we had 105 with positive label and 60 with negative label. So we had 105 cases with heart disease and 60 cases of healthy patients, of healthy people, in fact. It's not called patient. Okay. And how do you interpret true positive? So out of those 105 that were labeled as diseased patients, so your model could predict 100 as diseased patients, but your model could not predict 5 out of those 105 as diseased people. So you say your model predicted yes 100 times and no 55 times. So in reality, yes is 105 times and no is 60 times. Sorry, hang on. It should be, yeah, it's all good. Okay. Uh, I hope this is clear. So let me give you one more example. We go back to that snowball bowling example. We use same information and I construct this contingency table. Interpretation. So your model predicted 305 regular balls. What is this 305? Right? And 10 no balls. And out of these 10, the 2 were incorrect predictions. And out of these 305, 7 were incorrect predictions. And if you see along column, out of 300 regular balls, your model could predict 298 regular balls. And out of 15 no balls, 15 in the 0 class, your model could predict 8 no balls correctly. Okay. I think this is clear now. Okay, now we have a good understanding of confusion matrix. I'm going to define some of the metrics, some of the measures using confusion matrix. So we know true positive, true negative, false positive, false negative. Using these 4 quantities, we will define some measures to evaluate performance of classifier. So these 4 true positive, true negative, false positive, false negative. These are not measures, right? So these are the just some quantities coming from the output of a classifier, and we will use these quantities to define some measures. Okay, we start with again accuracy. If I ask you uh, that 1-0 loss accuracy, so 1 minus misclassification rate, if you want to find the same accuracy using your confusion matrix, can you find out? In fact, you can. So accuracy would be true positive plus true negative divided by total number of points. True positive indicates the number of positive points your model predicted as positive. True negative, number of points in class 0 your model could predict in class 0. So true positive plus true negative divided by sum of these four. So what you get is accuracy. So mathematically, we say that accuracy will be given by true positive plus true negative divided by total number of points you have. Uh, okay, misclassification or error rate, overall how frequently it is wrong. Mathematically, it is given by false positive plus, hang on, plus false negative divided by total number of points, or this is just 1 minus accuracy. Okay, so these are very obvious terms. Let's define some good measures or some practical measures. The first one is sensitivity. We also call it recall, and there is a reason why we call it recall. I will explain it shortly. And true positive rate. So how often does your model predict positive when it is actually positive? If I give you this confusion matrix and I ask you to compute this proportion, right? So we want to find out of all the positive data points, all the data points that had the gold label, how many have been truly identified as positive by our classifier? What are total number of points with one as gold label? TP plus FNP, right? And out of these P points, you could predict TP points. So a true positive rate or sensitivity or recall is given by simply true positive divided by true positive plus false negative. Right? In case you forget this formula, you don't need to, in fact, you don't need to remember this. You simply look at the table and you take true positive rate, you take true positive and you sum along that column and you get recall or sensitivity or true positive rate. So TPR is simply TP divided by the values of the column in which TP is present. Right? Simple. Let's also define some more metrics. False positive rate, as the name suggests. Right? So actual negative, how often does it predict positive? It's a false positive rate. Okay, I think now you're trained enough that you can compute this. It will be simply given by false positive divided by the number of points, so all the points in the column containing F false positive, right? Or FPR is given by false positive divided by total number of points with a label of negative class, label of class 0. Okay. Okay, let's talk about another metric, specificity or true negative rate. When it is actually negative, how often does it predict positive? So actual label is negative and you predict as positive. right? Where do you get it? Hang on. So it's a true negative rate when it's actually negative, and how often does it predict? It should be, my apologies. It should be, I will correct this in the notes. Negative. So true negative divided by n, and that is simply 1 minus false positive rate. Let's define some another metric which is very, very important, what we call precision. When it predicts positive, how often is it positive? What do we mean by this? You predicted as positive, and out of those positive predictions, so how often is it positive? That how many points out of the total positive predicted points had gold label as positive? And that will be simply given by, if you see confusion matrix table, you sum TP and FP, you get total positives predicted, right? And out of these total, only had TP is capturing TP number of points had the actual positive label. So precision would be given by simply a ratio of TP divided by predicted total positive, that is TP plus FP. So that's how we define precision. Okay. I hope this is clear now, right? So what do you, sensitivity, specificity, and precision? We will study these terms in detail. Right? So what is precision? When it predicts positive, how often is it positive? Sensitivity. So what was sensitivity? TP over TP plus Fn. When it is actually positive, how often does it predict positive? Okay. Okay, let's move forward. And let me summarize all of this from the confusion matrix. So we have this confusion matrix, and what is sensitivity? True positive rate. So TP divided by sum of all the terms in this column. TP over TP plus Fn. If you use the second column, right, and you use true negative divided by ratio, you get true negative rate, and which is also called specificity. So we have precision, which is simply true positive divided by a sum of these two. And this quantity is given by true negative divided by true negative plus false negative. Okay. So that is when it is negative, how often does the model detect it negative? Right. So you predicted total negative values, which are Tn plus Fn, and you divide Tn by this quantity. That means out of total predicted negative values, how many values had the label 0, had the label negative? Okay, let's compute these terms for the disease prediction example. Okay, we had this confusion matrix for disease prediction example, and we want to compute accuracy, misclassification rate, sensitivity, true negative rate, and precision. Okay, accuracy. How would you compute it? Total patients 165, true positive 100, true negative 50. So accuracy should be given by 100 plus 50 divided by 165. 0.91, right? Misclassification rate. Now 1 minus accuracy, right? 0.09. Sensitivity or recall. How would you compute sensitivity? And what's the interpretation of sensitivity? When it is positive, when you have a diseased patient, how often does the classifier detected disease? Okay, that is 100 by 105, that is 0.95. Okay. uh, False positive rate, so actually healthy, but your model predicted healthy. That is simply false positive by n, that is 10 over 60.17. Sorry, actually healthy, how often does it predict diseased? That is 10 over 60, because it's false positive rate. Your model predicted as positive, but that is a false prediction. In fact, it has a negative label. TNR specificity, 50 over 60, that is 0.83, and precision would be simply, you can compute it, 100 over 110.91. But you need to look at the interpretation of precision. Your model predicts disease patient. How often is it correct? Because you don't want all the patients to be incorrectly classified as diseased. So precision is important in disease prediction. You want to precisely classify patients as diseased or healthy. Okay. We have defined too many metrics, right? But I think we will keep on using these metrics, and you will be comfortable with these. The question here is, out of these metrics, when to use and which one to use to evaluate the performance of a classifier, right? To answer this question, maybe we start with a couple of examples. Right? So again, consider our disease detection problem, right? In this problem, we do not want to have false negatives. So we should take the metric out of all the metrics which have false negative in the denominator. And our model should give higher values for that metric. If you go back and see all the metrics, which of the metrics had false negative in the denominator? So if you recall, the true positive rate, right? So had Fn in the denominator. So true positive rate, sensitivity, recall. If you want to lower Fn, if you want to have less number of false negatives, you should be having high value of, you would desire the TPR to have high value. Okay. So what about this example? In fraud detection, you do not want false positive, right? So I'm assuming that fraud is considered as positive and not fraud is negative. So we need to be absolutely sure when we say it is fraud. We cannot afford to have false positives, in fact. Right? And when we do not want false positive, or we want false positive to reduce, we can use true negative rate as our metric, because in true negative rate we have false positive in the denominator. Higher value of true negative rate implies low value of false positive, right? Or instead of TNR, you could also use precision, because in precision we also have false positive in the denominator. Okay. Okay, so we conclude this video. We have talked about the issues with the accuracy as a measure to evaluate performance of a classifier. When we have imbalanced classes, when we have skewed classes, we should not use accuracy as a measure. And then we defined true positive, true negative, false positive, false negative. Using these terms, we construct a confusion matrix, and from the confusion matrix, from these using these four quantities, we defined a couple of new metrics to evaluate the performance of classifier. Okay, we will stop here, and in the next video, I will talk about the trade-off between these metrics, especially the trade-off between precision and recall, precision and sensitivity, and sensitivity and specificity. And how do we study, how do we analyze these trade-offs? Okay, we'll stop here and see you in the next video, inshallah.